Today, we are going to talk about some theorems about parallel lines. These problems are not going to be directly related to parallelograms, even though they're in this chapter. The reason why they're in this chapter and right now is because if we would actually go through the process of proving these theorems, we would need parallelograms to do the proofs, and I'll point that out to you, kind of what that would look like when we get to one of our example problems. So that's why they're here, but it's going to maybe feel a little bit strange since they're not about parallelograms, and that's what we've been talking about so far. So it will probably be helpful, at least for those of you who are visual learners, but I think probably for almost everybody to have pictures of these. So I'll draw a picture for each one of the theorems, but we're not going to prove them individually today. If two lines are parallel, it says then all points on one line are equidistant for the other line. Now, I really don't like the wording of this theorem because it says something, I think, that's not really totally right. Because it says if I take all points on the one line and any points on the other line, they're equidistant. But that's not really true because this one isn't the same distance as that one. What this theorem means is if you connect the two lines in the shortest way possible, that will always be the same. Okay, so when it's talking about that equidistant, it's meaning the shortest possible distance. That would always be the same. But it's not just that you can take any point on one line and connect it to any point on the other line. Those wouldn't necessarily always be the same. But if you always connect in the shortest way possible, then those distances will always be the same. The next one says if three parallel lines cut off congruent segments on one transversal, then they do that on every transversal. So if I have three lines that are parallel in such a way that I draw in a transversal and I get some equal pieces, that will be true of any line that I draw through that crosses them. Now you cannot make comparisons from one of the transversals to the other transversal. There's nothing that connects that information. But along one single transversal, we're going to get equal pieces then. Theorem 510 says a line that contains the midpoint of one side of a triangle. So here's my triangle. I'm going to make a midpoint, and I'll call it M. A line that contains the midpoint of one side of a triangle and is parallel to another side. So I'm going to make it parallel to the bottom. It says passes through the midpoint of the third side. So we know if it goes through one midpoint and it's parallel to one side, it has to go through another midpoint, is what Theorem 510 tells us. If it goes through one midpoint and it's parallel to one side, it has to go through another midpoint. So both M and N are actually midpoints of their sides.
Oh, so that the hypotenuse would be equal sides to them.
Yeah, it's not really hypotenuse because it's not a right angle, but the side with M on it there,
That's what
yes, would be equal as well. Theorem 511 starts almost as a converse to that. It says the segment that joins the midpoints of two sides is parallel to the third side. So in drawing that out, we get pretty much the same picture, it's just different given information. In Theorem 510, we knew we had one midpoint in a parallel. In Theorem 511, we know starting out that we have two midpoints. And it turns out that it really works both ways. But Theorem 511 gives us one extra piece of information, and we'll go ahead and label these points out again, that NM is equal to half the length of XY. So if NM is X, then XY would be twice that big. That we could call that little segment a median segment, and it will be equal to half the length of the side that it is opposite of.
Wait, NM is equal to X? I don't
Maybe X is a bad letter to use as a point here, and then we'll call it Z. So that if NM has a length of X, then that other side has a length of twice of x, is what this theorem says. Okay, so that median segment has half the length of the side that it is across from. And that is the theorem that we're going to use in most of our example problems here.
Good thing no one's gonna watch it on my phone for a while.
Okay, so I've got a few example problems up here now. We are given in this problem that points T, N, and M are midpoints. So of those three sides of the large triangle then, we know we have midpoints. So that means that those last two theorems apply to this picture, that we've got midpoints connecting, we know we would then have parallels, and we know that those median segments are going to be half the length of the side that they're across from. So in our problems then, the first one says, if xz is 10, so if this whole side is 10, then mn is what? 5. Now the reason why these theorems were included in this section is when we draw in all of those median segments the way that this is, we get this little picture inside of here. And one of the things that those theorems told us was that those median segments should be parallel to the line that they're across from. So inside of there, what little shape do we get? A parallelogram. And what do we know about opposite sides of parallelograms? They're parallel and they're congruent. So if the whole of xz is 10 and I have a midpoint, then this part would have to be 5. And opposite of that would then have to be 5 as well. So that's why these theorems are included in this chapter, even though they're about triangles and not parallelograms, that really in there we can actually find a connection to parallelograms as well. The next one says if Tn is 7, then how big is xy? 14. Because the median segment should be equal to half the length of the segment it is across from. The next one says if Zn is 8, then how big is Tm? 8. Because Zn is half of that full side xy, and Tm is supposed to be equal to half of that full side. So those should both be 8. And the last one, if xy is k, then Tn is what? Half of k. Or k divided by 2 would be another way of writing that same thing. Okay? So you will have several problems like this in your assignment. There's one other type of problem that you will have several of, and that is you will have some parallels. 4. Oh, this is fun. And we will know that those parallels are cutting these transversals in such a way that they're making congruent segments. So if I know that this little piece is 7, how big is it from A to B then? 21. Because each of those are the same length. According to the picture, they're each marked as the same. So 3/7 makes a 21. If I know that this part is 4, how big is it from C to D? 8, because it's 2 4s put together, okay? But notice that you cannot make a connection between lengths on the segment AB and lengths over on the segment CD. We cannot relate one transversal to the other, but along a transversal, we can know that we're getting equal pieces there. Okay?
Yep.
Questions? Okay, your homework is from section 5.3 tonight.